Ever get that frustrating lag when you're trying to open a massive file or like switch between a bunch of apps?
Oh, tell me about it.
We blame the spinning beach ball, the loading icon.
Yeah.
But I'm here to tell you, there's a silent hero working behind the scenes, or should I say, a silent memory. Today's deep dive takes us into the fascinating and often overlooked world of computer memory. We're using Ulrich Drepper's What Every Programmer Should Know About Memory as our guide.
And don't worry, we'll translate the tech speak so you can, impress your friends with your newfound knowledge.
Okay, so RAM. We all hear that acronym, but what's the deal with the different types? It's not a one-size-fits-all, right?
You got it. Imagine, two types of notepads.
Okay.
One is like a sticky note, super fast to jot down and read information, but you can't fit much on it. That's SRAM. Static RAM.
RAM too.
It's expensive, but it's what your processor uses for, its fastest calculations. Then there's DRAM, dynamic RAM, your computer's main memory. Think of it like a giant whiteboard. Plenty of space, but it takes a bit longer to write or erase things.
So SRAM is like the quick notes. DRAM is where we store the detailed plans, but it's a bit slower to access.
Yeah, exactly.
Makes sense. But you said DRAM is like a whiteboard. What's the catch?
Yeah.
Whiteboards don't really erase themselves, do they?
Good point. DRAM is a bit like, a leaky faucet.
Leaky faucet.
It uses these tiny capacitors that store electrical charge, which represents data. But the charge leaks away, and if it's not refreshed constantly, you lose the data.
Oh, no.
Those refresh cycles take time, which impacts how quickly DRAM can deliver that information to the CPU.
So our computer memory is constantly forgetting things and needs reminders. That's wild.
Yeah.
No wonder it's slower than SRAM.
It's a constant balancing act between speed, cost, and this quirk of physics.
Right.
And to make things even more interesting.
Oh, no, now.
DRAM chips use a clever trick called address multiplexing to, squeeze the most out of the available space.
Multiplexing. That sounds complicated.
Think of it like an apartment building with one elevator.
Okay, I'm with you.
To get to a specific apartment, you need the floor number and the apartment number.
Right.
In DRAM, the address of the data is sent in two parts, kind of like telling the elevator first the row, then the individual memory location.
Okay.
This sharing of the address lines saves resources, but adds a tiny delay, just like waiting for the elevator to make two stops instead of one.
So it's a bit of a trade-off, slower access in exchange for more efficient use of space and resources.
Exactly.
Clever, but maybe a bit frustrating when you're waiting for that elevator or data to arrive, and I'm guessing those delays add up.
You're right, those tiny delays matter, especially as processors get faster. And that brings us to another clever trick. DDR SDRAM.
DDR is SDRAM. Okay.
Which stands for Double Data Rate Synchronous Dynamic RAM. It's like that elevator suddenly becoming twice as efficient by transferring data on both the up and down movements.
So instead of just using the up cycle, DDR squeezes in twice the work by using both the up and down cycles.
Yeah.
That's some clever engineering.
Exactly. But even with these advancements, the fundamental speed difference between DRAM and the CPU remains. Which brings us to a vital component called the CPU cache.
Okay, so DDR SDRAM helps speed things up, but we still have this gap between our super fast CPUs and our slightly slower DRAM. It's like having a race car driver stuck in rush hour traffic. How do we solve that?
That's where the CPU cache comes in a brilliant little invention that makes your computer feel much faster than it actually might be. Imagine your CPU is a chef and DRAM is the pantry. The chef needs ingredients constantly, but running back to the pantry for every single item would take forever.
Talk about a slow kitchen. What's a chef to do?
That's where the cutting board comes in. That's her cache. It's a much smaller, super fast memory area right next to the processor. It stores the most frequently used data and instructions so the CPU can access them instantly without waiting for the slower DRAM.
So it's like having your most used ingredients prepped and ready to go right on the counter. No more running back and forth to the pantry for every little thing.
Precisely. And just like a well-organized kitchen, CPU caches are divided into levels. You have the L1 cache, which is like having a few essential ingredients right next to the stove, incredibly fast but tiny. Then there's the L2 cache, a bit bigger and a tad slower, like a countertop for more ingredients. And some systems even have an L3 cache, even larger and shared between multiple CPU cores.
So it's like having different levels of readily available ingredients with the most important ones closest and the less frequently used ones a bit further away, but still more convenient than the main pantry.
Exactly. And of course, there are times when the CPU needs something that's not in the cache. That's called a cache miss.
I'm guessing those aren't ideal. Like when you realize you're out of salt mid-recipe.
You got it. A cache miss means going all the way back to main memory, which is relatively slow. So minimizing those misses is crucial for performance.
Makes sense. How do we make sure the cache is stocked with the right stuff? Do we get to choose?
Well, you don't get to choose directly, but the software you're using and the way it's programmed plays a big role. Think about it, even with the best cache system. If the software is constantly asking for data that's scattered all over the place, you'll have a lot of cache misses. It's like having a messy kitchen where you can never find anything.
So software developers are kind of like kitchen organizers, trying to keep things tidy and efficient for the chef, aka the CPU. What are some of the tricks they use to make sure the cache is used effectively?
One crucial aspect is data alignment. It's like organizing your ingredients in a way that makes sense. If data is aligned with the way the cache works, it's much faster to access. Think of it like having all the ingredients for a specific dish grouped together on your counter.
So instead of having to grab a pinch of this from here and a dash of that from there, you have everything you need in one place. That makes sense.
Exactly. Then there's minimizing cache lane conflicts. Cache lanes are like those containers on your counter, each holding a specific amount of data. If two frequently used pieces of data end up in the same cache line, they'll constantly be swapped in and out, leading to more cache misses. It's like having to constantly rearrange your containers because you need something from the bottom one.
So efficient data organization is key. It's all about making the most of that limited cache space. What else can software developers do?
They can use a technique called prefetching. Think of it like anticipating what ingredients you'll need next and getting them out of the pantry in advance. Software can give the CPU a heads up about what data it will need soon, allowing it to start fetching it from DRAM before it's actually needed.
So it's all about anticipating the CPU's needs and minimizing those trips to main memory. And we talked about RAM and CPU caches, but I have a feeling there's more to this memory landscape, right?
You're right. As systems become more complex, with multiple processors and even more cores, we encounter new challenges. And that's where NUMA comes in.
EUA, that sounds intriguing and a little intimidating. What does that stand for, and what's the concept?
NUMA stands for Non-Uniform Memory Access.
Non-uniform memory access, okay.
It describes the layout of memory in, more complex systems, those with multiple processors or a large number of cores. Imagine you have a giant kitchen with multiple chefs, each with their own workstation. Now imagine that instead of one central pantry, there are smaller pantries located closer to each workstation.
Okay, so a bit like having a mini pantry for each chef to reduce those long trips to the main one. That makes sense, but what makes it non-uniform?
That's the key point. Some pantries might be closer to certain workstations than others.
Okay.
So accessing ingredients from a nearby pantry is much faster than having to go to one further away. In a NUMA system, memory access time depends on the location of the processor and the memory it's trying to access. It's not all equal anymore.
So it's like some chefs have to walk further than others to get the ingredients they need. That sounds like it could lead to some uneven cooking times.
Exactly. And just like a smart kitchen manager would try to optimize the layout to minimize those distances, software developers working with NUMA systems need to be mindful of where data is stored and how it's accessed.
So another layer of complexity for those developers to juggle.
Mhm.
But you mentioned virtualization earlier. We've talked about physical memory, but what happens when we have virtual machines sharing those resources? Does it change the game?
It definitely adds another layer of complexity. Imagine trying to run multiple virtual kitchens within your single physical kitchen.
Okay.
Each virtual machine is like its own self-contained environment with its own operating system and applications, thinking it has its own dedicated resources.
So it's like having multiple chefs trying to share the same kitchen space, each thinking they have full reign of the pantry and workstations. It sounds like a recipe for disaster.
It could be, but luckily virtualization platforms like XZen and KVM have clever ways to manage these shared resources. They act like the ultimate kitchen manager, allocating physical memory to each virtual machine in a way that makes it seem like they each have their own dedicated space.
So it's all about creating the illusion of independent kitchens, even though they're all sharing the same physical space and resources.
Precisely. And this memory management is essential for virtualization to work efficiently. Without it, those virtual kitchens would be constantly bumping into each other, slowing everything down.
This deep dive has been eye-opening. We've gone from leaky faucets and crowded elevators to chefs battling for pantry space. I never imagined the world of computer memory could be so intricate and fascinating.
It's a testament to the ingenuity of the engineers who've developed these complex systems and the programmers who optimize software to work within these constraints.
Absolutely. Well, on that note, thanks for joining me on this deep dive into the world of computer memory. I hope you learned something new and maybe even feel inspired to, upgrade your RAM or finally clear out those unused apps. Until next time, happy computing.